Hello everyone, I'm J Wildberger, and this is part of a series on the sociology of pure mathematics. If you're a social scientist and you're interested in understanding this phenomena of pure mathematics, having an appreciation for the history and the cultural spread across the world is really valuable. Mathematics is a very old and established subject, much more so than most of the other sciences, especially the physical sciences. The only thing that can really compare is medicine in terms of how long this discipline has been studied. So today I want to give you an overview of some of the early history of mathematics and with a view of how pure mathematics fits into this. So I'm going to be comparing the pure and the applied directions, even though maybe we're not entirely clear as to what that distinction really is. So almost surely the origins of mathematics lie in antiquity via the arithmetic of commerce, trade, barter, exchange. The theoretical side of that is number theory, which say involves things like primes and factorization, triangular numbers, special numbers like that. That actually is a relatively recent development around the Greek period, maybe starting around 500 BCE. Today we're interested in the origins of geometry, which roughly could be phrased in terms of astronomy, surveying, and construction issues. Those are three broad areas in which geometry appears. And time-wise, there is already evidence for this in the Mesolithic period, starting around 10,000 BCE, and then moving into the Neolithic period from around 7,000 to 3,000 BCE. And at the end of this, the advent of the great early civilizations like the Egyptians, the Mesopotamians, the Chinese, the Indians, and so on. So early cities starting to appear at the end of this period. So it's a very rich time frame. The origins are a little bit murky. There's a lot we know, but a lot more that we don't know. If you're interested in these topics, my math history series has a lot of videos that cover some of these things in more detail. I also have a series on ancient mathematics, which I hope to do more videos on. And there's another one on Old Babylonian Maths and Plimpton 322 with Daniel Mansfield, where we look at a particularly fascinating cuneiform tablet. What can we say about the earliest sort of theoretical development in geometry? Well, it's speculative, but I think that it probably has to do with the 3-4-5 triangle. This is an elementary but remarkable configuration that goes back in time beyond as far as we can see into history. So it's a triangle whose sides have lengths 3, 4, 5, and if you tighten these ropes perhaps, or create some boards to make this triangle, then you will see that these two sides here, the smaller sides, are exactly perpendicular. And this is a way of establishing perpendicularity using, say, ropes that surveyors actually used in the Old Babylonian period, probably in the Sumerians, probably the Egyptians also. So this 3-4-5 triangle, we see aspects of it in a lot of cultures and in a lot of even earlier monolithic constructions. So it seems to have somehow been almost a universally understood phenomena. Talking with Howard Crowhurst, and you can see some of his discussions on my ancient mathematics series, the Carnac alignments in France, these fabulous arrays of monolithic stones, they definitely suggest quite a strong familiarity with this right triangle and actually some other ones as well. And certainly the Egyptians, the Sumerians, the Indians, the Chinese, they all knew about this special triangle. And of course, this is related to the most important theorem in mathematics, which these days is called Pythagoras' theorem, but was known more than 1,000 years before Pythagoras was even born by the Old Babylonians, and very possibly by the Egyptians too, although we don't know that so well. But the Babylonians referred to it as the diagonal rule, and it states that if you have a triangle, like that one in there, and you construct squares on the three sides and measure the areas of those squares, say A, B, and C, then the perpendicularity of those two sides manifests itself in this arithmetic relation that a plus b equals c. And conversely, if a plus b equals c, then you have perpendicularity there. So this is the most important and famous theorem in mathematics, and it's been known at least since the old Babylonian period. And of course, this is an example of it, because if you create the square here, it has an area of 16. Here's an area of 9. Here there's an area of 25. And yes, 16 plus 9 does equal 25. But a proof of this, so establishing this as not just an observationally correct fact, but actually as a logical consequence of some prior geometry, that had to await the ancient Greeks. And Book 1 of Euclid is very much interested in establishing this important result. But I don't want you to get the idea that early geometry was theoretical. Far from it. The main thrust of geometry in ancient times was applied. And broadly, we can identify three main areas in which it figured prominently: astronomy, surveying, and construction. So astronomy was hugely important for ancient peoples. Almost all major cultures had a preoccupation with the night sky, the celestial sphere of stars and how it moves around during the night, and then the motion of the sun and the moon and these planets on this sphere of celestial stars. Okay? So understanding that was a main preoccupation for almost all major cultures. And people were interested in mapping stars. The Chinese, for example, created elaborate maps of stars and constellation. They were interested, of course, in the motion of the sun and the moon, because the sun and the moon are moving on this ecliptic plane, which sort of cuts across the night sky in a sort of a semicircle. And the moon, of course, is moving visibly along that during the night. But and so is the sun. But as you observe the moon over a period of a month, it will kind of make a complete transversal of this thing. And if you watch more carefully, the sun is actually also moving along this thing once a year. So the sun and the moon have some motions that can be detected with careful observation. More interesting, perhaps, and more surprising is the motion of these planets, these curious things which are like stars, but they're definitely not like stars because they're actually moving. We're talking about Mercury, Venus, Mars, Jupiter, and Saturn. Okay, these are the ones that are potentially visible to us in the night sky if things are in the right positions. And they also move on this ecliptic plane, but they do so in a much more a random kind of way, like they move along in this direction, then they stop and kind of wander back, and then they keep on going. So trying to understand what they were doing was a major preoccupation. And of course, people had this idea, maybe somewhat mystical or connected with religious ideas, that the motion of these various players on the celestial sphere somehow affected earthly doings. So it was important for religious purposes to keep track of things. But it was also a kind of a timekeeping. So in terms of timing harvests or floods, these things were important to understand the motions of these things. Of course, predicting eclipses is kind of a spectacular consequence. If you can understand things so well that you can predict eclipses, then you impress a lot of people. Another important use of geometry was in surveying, especially having to do with field plans. So if you're in the Nile Valley, which floods once a year, then everything gets sort of washed out, and then you have to reestablish whose fields go, as far as they do, and where does the neighbors start, etc. So surveying was an important part of that, and even in the old Babylonian times, we have a lot of field plans on cuneiform tablets where we can see what the surveyors were doing. In particular, it's a very interesting one called Psi 427, which is in the Istanbul Museum, which has been studied recently by my colleague Daniel Mansfield, where he discovers really interesting geometry, very early use of diagonal triples. These are these things coming from the Pythagorean theorem. He sees that they're actually using these as a tool to construct perpendicular lines in field plans. So there's definitely an application of geometrical ideas in the old Babylonian times to this practical problem of surveying. They're also interested in area formulas. They're interested in subdivision problems. You have a triangle, a farmer has a triangular field, and he has to divide it equally amongst his 5 sons. How does he do it? Things like that. And then there's construction. So this is a little bit different because we don't have direct written evidence often, but we have remains. We have remains of a lot of monoliths scattered around Europe, Asia, other places. And notably, we have all this fabulous building and creation in Egypt, okay, which is absolutely mind-boggling, which really suggests a very sophisticated understanding of geometry. Although we don't actually have written records that supports that, but any even casual observation of these pyramids and tombs and various things that they built makes it clear that their understanding of geometry was already at a very high level, because there's no way you can build these pyramids and create these shafts and these air shafts and all these intricate things without thinking very clearly about the 3D problem of how all these things are going to fit together. As you're constructing this, it's going to take you 20 years to construct this, and you have to do it all in an exact fashion. So you have to be really sophisticated geometrically. So it's a case that we don't have the actual written evidence, but the evidence is there for us in stone, for us to verify that they were very sophisticated geometrically. In the old Babylonian side of things, they built out of clay, unfortunately, and very little of that is left over now. But almost surely they had remarkable cities and temples and canals and palaces and so on. That would perhaps have rivaled some of the Egyptian constructions. But we do have more written evidence in the old Babylonian Sumerian area. So certainly construction is another important application of geometry. So these 3 are areas where geometry is really being used in an applied setting from very early times. Now when we get to the Greek period, starting roughly 500 BC and proceeding up to 300 or 400 AD, we see definitely a shift towards also pure or theoretical or abstract geometry. And just a few highlights. There was a lot done, but just a few highlights. Certainly the investigation of the Platonic solids was a very main subject of interest. There's 5 Platonic solids: the tetrahedron, the cube, the octahedron, the icosahedron, and the dodecahedron. The dodecahedron is arguably sort of the most well-studied and maybe revered one. It consists of these pentagonal faces, and there's one on top, one on the bottom, 5 here and 5 there. So altogether 12 of these pentagonal faces, and they all fit together exactly to form this remarkable solid called the dodecahedron. And Plato already talks about the beauty of these things, and in Euclid's Elements, which of course is concerned with all kinds of aspects of pure or at least abstract geometry, there's a lot of things being done, as we've talked already about, but one of the definite aims of Euclid is to understand aspects of the geometry of the Platonic solids. In one of the last books, maybe it is the last book, he reserves his attention to finding out all kinds of interesting facts about things like the dodecahedron. But there's other results too, there are other work that's very important. The Apollonius, perhaps the greatest geometer of the Greek period, made a thorough investigation of conics, which is really important. And then there's a later result due to Pappus, which we should mention because it's historically really interesting and sort of the first step to an entirely new kind of geometry, different from all the Euclidean kind of geometry that had preceded it. So amongst the results, let me just mention 3 of them. Here's Thales' theorem. Thales was a very early Greek mathematician, perhaps the teacher of Pythagoras, and he discovered that if you take a circle and you take a diameter of a circle and any other point on the circle and join up the lines like this, then you're always getting a perpendicularity there between these 2 sides, no matter where this third point is. Apollonius, in his investigation of conics, discovered a remarkable polarity or duality between points and lines in the plane that is determined by a conic. This is a particular case of that where this is the focus of this ellipse, and that's the directrix, but it's actually just a special case of actually a remarkable kind of polarity. You choose a point, and then there's an associated polar line. If the point is outside, well, then the line will be sort of inside like this, okay? And that's quite interesting, but sort of a theoretical nature. And then this Pappus's theorem is really interesting because it's really the only theorem in ancient Greek times which is demonstrably disassociated from Euclidean geometry in the sense that only the straight edge is being used. The compass is not involved at all. So the conic sections are sort of created from circles. That's the way the Greeks thought about them. But this is purely a result having to do with straight lines. So there's a straight line, there's another straight line, 3 points A, B, C on this line, 3 points A prime, B prime, C prime on that line. Then you join A and B prime and A prime and B, and you get a point of intersection. You join B and C prime and B prime and C prime, you get a point of intersection. So that's just C, B prime and C. And then you also join A and C prime and A prime and C, and you get a point. So you get these 3 points of intersection, and lo and behold, they always lie on a line. So they didn't realize it at the time, but this is actually the first and probably the most important theorem in projective geometry, which came into existence really only much later in the 17th century with the work of Desargues and also Pascal, who famously generalized this to apply to a conic. And then in the 19th century, people started to understand projective geometry much better, and then it became suddenly a huge and beautiful discipline that almost sort of embraced a lot of the existing geometry up till that time. So there's a whole wealth of really interesting, pure theoretical, abstract geometry that the ancient Greeks were interested in and that they discovered. But it's important to appreciate that in the Greek period, there was also a great interest in applied geometry. So we can mention, amongst many things, the work of Eratosthenes, who was the chief librarian in Alexandria at the library there, and also perhaps the world's first great geographer. And he was able to calculate, approximately, distances to the sun and the moon by making very clever observations on Earth and actually using the geometry of the Earth, the geography of the Earth to make that. Those are discussed in Famous Math Problems 9 if you're interested in his work. And then there was Archimedes, this towering figure of ancient Greek mathematics, who also discovered lots of theoretical things in geometry, but famously also was very interested in practical or engineering or applied things that had to do with measurement. Euclid sort of famously avoided measurement issues, but Archimedes loved to think about measuring things. And in particular, he was the first person to come up with incredibly beautiful formulas for volumes and surface areas associated to spheres. And in Famous Math Problem 6, I also discuss his parabola quadrature theorem, which is pretty well the first major theorem in calculus, long before Newton, Leibniz, and their fellows. So the parabola quadrature theorem is like this. Here's a parabola, which is a particular conic section. It's like an ellipse, but it doesn't have sort of an endpoint out there. And here's 2 points on the parabola PQ, and then this line determines this parabolic arc. Okay, and we're interested in the parabolic arc and its area. And Archimedes discovers that the area of this parabolic arc is actually 2/3 the area of this triangle PQR, obtained by looking at the tangents to the parabola at P and Q, and where they meet at this point R. Right? So here's a triangle which just has an ordinary area. You calculate that ordinary area, and you take 2/3 of it, and miraculously you get this area of this parabolic arc. And that doesn't matter where the points P and Q are on the parabola. So absolutely remarkable result, and really is really perhaps the first result in calculus. It's a calculus result. Now there are 2 other ancient civilizations that we should talk about, the Chinese and the Indian. So the Chinese have also a long history, especially of development of astronomy. they had all kinds of remarkable things that they discovered in astronomy. In terms of geometry, maybe their interests were not so much in that direction. They were also very interested in algebraic and arithmetical things like solving equations. The Indian story, emanating, say, from around 1500 to 500 BCE, that's the Vedic period of Indian geometry. There's constructions of altars there. They're interested in geometry. These altars and their sort of geometry, making sure this geometry is perfect in some sense, figured very prominently in their thinking. And the Pythagorean triples figure there too. And then later on, there's a classic period from around 500 to 1300 AD, where there's a great profusion of interesting work, a lot of astronomical work, including early sine tables. And in terms of geometry, we can mention Brahmagupta's formula, which concerns the area of a cyclic quadrilateral. That's a quadrilateral whose 4 vertices sit on a circle. And if the side lengths of this thing are A, B, C, and D, then his formula is that the area is equal to the square root of the product of S minus A, S minus B, S minus C, S minus D, where S is this semi-perimeter. It's half of the way around. So A plus B plus C plus D all over 2. And it turns out that this is a generalization of an earlier formula usually attributed to Heron, though it probably goes back to Archimedes, for the area of a triangle. So there's a very similar formula for the area of a triangle that students used to learn in high school, but they don't anymore. And anyway, this is an indication of the quite evolved aspect of Indian mathematics. And so I just want to say a little bit also about the later development of Islamic or Arabic mathematics. So this is in the period 800 to say 1500 AD. The Prophet Muhammad creates the Islamic world, then an empire rapidly disseminates across the Middle East, into North Africa, and ultimately even into Spain. And it becomes a center for learning. It was centered around Baghdad, and a lot of ancient Greek manuscripts and also Indian works are brought together and studied intensively. And then the Islamic mathematicians, who are spread across a very wide area, make all kinds of interesting further developments. And these spread, from modern-day Uzbekistan to Egypt to, of course, modern-day Iraq and the Middle East generally, and even all the way to Spain. So they were very interested in astronomy and associated spherical geometry because, of course, the dominant object in astronomy, they thought, all ancient peoples thought, was this celestial sphere. This sphere which we are at the center of the fixed stars, which is rotating around every night. Okay? And the geometry of this was the main object of interest because that was the domain upon which the movement of the sun and moon and planets was taking place. Now, spherical geometry is unfortunately not much studied these days, but one should appreciate that for thousands of years, spherical geometry was more interesting and more important and more studied than planar geometry because of its evident connections with astronomy. So remember that for a lot of history, astronomy and mathematics were tied very closely together. So the story is like a sphere, okay? A sphere, and for example, a basic object of study is a spherical triangle formed by 3 great circles. Great circle is what you get when you slice a sphere with a plane that goes through the center of the sphere. That's a great circle. So it's like a largest kind of circle you can draw on the surface of the sphere. And if you have 3 of these, then typically it will create this triangle. So if we take this triangle, sort of put it over there, then we can say, aha, this triangle has 3 sides, A, B, and C. And you can think about those as sort of lengths, but they're kind of lengths which are curved. And so we end up thinking about them as being sort of associated with the angles subtended by those arcs at the center of the sphere. And then we have the actual angles formed by the lines where they meet at the vertices. So there's actually really 6 sort of angles floating around here, while 3 of them are interpreted as distances. And then the spherical triangle leads us to this question of spherical trigonometry, which is to describe the relations between these 6 things. And, and the Arab Islamic mathematicians made great strides in this direction. So the law of sines was introduced by several people, but maybe including Bujani. The law of cosines, sometime later by Al-Tusi. And these formulas are first established in the spherical case, and then later on, almost as side issues, the planar versions are enunciated. But these days, the planar versions are what's taught to high school students, and the spherical versions are almost entirely lost. It's a very interesting sociological point, how this shift has taken place, how this vast subject of spherical geometry has all but disappeared in the modern curriculum, even though it was a central object of study for literally thousands of years. And to an Islamic scholar, it would be intrinsically more interesting, just much more interesting and more important. So that's a brief view of the history of geometry up to the European times. So in my next video, we'll go on and talk about geometry in the European times. Hope you'll join me for that. I'm J Wildberger. Thanks for listening.